Oh, great, we're off and running. How do I unmute this? Is this the magic button? Okay, I'm unmuted. Off I go. Okay. I am not Alice. I am Tim. and I am here to present the presentation about enabling application portability across HPC platforms and application perspective. Okay, so Alice couldn't make it, so she sent me some slides. And so I'm going to present her slides, which, well, okay, that's kind of exciting. How do I advance it? Why doesn't it work? Oh, I have to push a different button? Which button did you push?
Black.
Oh, okay. You know, once you change over to Macintosh, going back to Windows is like, oh, this is really weird. Okay, so look, I always like to start with a disclaimer because, you know, I work in a corporation and we're always afraid of getting sued. So these are my views. And actually, these are the views of some of the slides of those co-authors, but we're not representing our employers. So don't sue NERSC or the DOE, and please don't sue Intel. I work with really smart people. I'm not one of those. So if I say anything stupid, it's all me. Don't go back to my collaborators and blame them on my stupidity. I work in Intel's labs. I know nothing about Intel products. There's a few slides where I talk about Intel products, but I really know nothing about them. I get to just think silly thoughts, point into dark corners, try and imagine what might be important down the road, and think about all that stuff. So it's really a lot of fun. I have a great job. So look, this talk is something, I'm trying an experiment. So I was sent these slides from Alice. What this really is, though, is a conversation between two talks. So we're going to move back and forth between my own slides and the slides from the NERSC crowd. And they'll be sort of talking to each other. And you'll always be able to tell when it's me and my slides talking to you because there'll be a picture of someone in a kayak. If you see a kayak picture on the slide, you know it's me talking, not my friends from NERSC. All right? I want to be really careful because I'm scared to death of the DOE office in Washington coming down and nailing me. So I'm really nervous and gun shy right now. So I want to be really clear when it's me talking, not speaking for the NERSC folks. And so you can tell because there'll be the kayak pictures. And if you don't know, I am obsessed with kayaking. And if you want to be bored for an hour or two, just ask me a question about kayaking. But we won't do that now. Oh, off we go. So let's talk about Cori, which is it's a pre-exascale supercomputer that'll be going in at NERSC. We're really excited about it. The idea is to try and push this continuing drive to more energy efficient architectures, more scalable architectures. And this is kind of seen as a showcase for technologies on one of the swim lanes to exascale. And yes, indeed, this is one is using, sort of the Intel swim lanes, where we're going to have lots and lots of slower cores, but larger numbers of them, and they're going to have great big honking vector units on them because everyone loves vectors. And very deep memory and storage hierarchies. So that's going to be the Cori machine. And I just want to point out, as a chemist myself, I am really pleased that they are naming their machine after a chemist. Because we all know chemists rule, right? I mean, have you ever met a chemist you didn't just fall in love with right away? They're awesome. So bravo to NERSC for naming your machine after a chemist. That's great. So there will be over 9,300 nights landing compute nodes, 1,600 Haswell compute nodes in the data servers, the Aries Interconnect, which I know nothing about except it kind of comes to us through Cray and Intel and is really, really fast. Lustre file system, it's really, really cool, but wait a minute. I'm the Intel guy. I guess I should be talking about the hardware. So let's divert here and let's talk a little bit about Knights Landing. Now, I'm going to tell you something. Xeon Phi never really did anything for me as a coprocessor. Sorry, Intel folks. Great, put it out there as a coprocessor, but if I have to go and move everything from my CPU across PCI to this coprocessor in order to do some computing, that's just, no, give me a break. I'm not going to do that. But take that many-core chip and put it in the socket. Now, all of a sudden, I am darn excited about it. Let's do something more. Let's take some DRAM, MC DRAM, multi-channel DRAM, right? Multi-chip DRAM? Okay, great. Multi-chip DRAM. I don't speak acronym, which is funny because everyone at Intel does. But let's put some DRAM right on the package. So it's really, really a cool idea. 36 tiles, 2D mesh, 2 cores per tile with 2 vector units. You know, if you didn't love vector units enough before, now you're really going to love them because we have 2 512-bit vector units per core, which is a scary thought. So another cool thing, so you have this mesh interconnect, so you don't have the huge network diameter of the original Xeon Phi. So this is a huge impact on the behavior of the network on a chip by having this, this 2D mesh. It's XY routing, so I guess that's all I'll say. Okay, I won't. There's routing algorithm stuff I could go into, but I won't. And it's cache coherent. So you can have a shared address space scheme, and it's really cool. Now, when you have that many cores with that much cache coherence, you need different ways of slicing up and organizing it. So we have these different ways of clustering modes, we call them, for putting together the cores. And so it's going to make, basically, as programmers trying to figure out how to develop and optimize code, there's an awful lot of dials we can play with and adjust on this chip to explore how to get the most advantage out of all those cores in the memory. And it's going to be a lot of fun. Another thing that I am personally incredibly excited about, and I don't say that facetiously, is the fact that we're going to put the network interface component right on the package. The marketing name for it is OmniPath, which is great because OmniPath is cool, I guess. I wonder about these names they come up with, you know. OmniPath, yeah, okay. But the fact is you have it on the package. I'm hoping someday it's on the silicon. You know, you're seeing a trend in computing going back many, many years, which is the CPU is like a Borg, sucking everything up, right? On your laptops, we've sucked up the GPU onto the CPU, right? As you learn more and more about how things work and what accelerators work, we suck them into the CPU. And so we see this NIC being sucked into the CPU, which is great because in an energy-constrained and latency-constrained world, the closer you can get everything integrated on that single piece of silicon, the better. Because it's a lot of energy to push electrons over a wire from one chip to another. So I see this as a very, very exciting development with the interconnect. So, and that, by the way, that's me being sucked down into a whirlpool. So it was pretty cool. Someone just happened to be at their camera right at the right moment. So at any rate, Knight's Landing, you know, programmers are really excited about it and really scared by it. All right? The optimization bozos like me are really excited because I have these different cache models. I can have a flat model. I can have a hybrid model for how I deal with that memory in a chip. And you've added these extra interesting features to the memory hierarchy. Of course, application programmers are also looking at that and going, oh my God, I couldn't handle 2 levels of cache, and now you're putting these extra levels of cache in an MCDRAM, and what's going to happen when we put NVRAM on the package? So, you know, you better learn to love complex mucking around in the guts of a memory hierarchy because there's going to be an awful lot of options out there, which is going to be a lot of fun. So I'm really excited about this. And I'll push the right button. Whoa. No. What did you do? See, I should have used my own laptop.
You don't need glasses anymore.
Well, I have weird eyeballs.
What did you do? Yes.
And now it's all out of order. And where am I? Okay. There. Okay. Whoa. So to run effectively on Cori, programmers are going to have to deal with multiple domains of parallelism. You're going to have to deal with MPI, but that's cool. Every single one of us in here loves MPI, right? Who doesn't love MPI? I mean, really? Well, you're wrong. MPI is awesome. Okay. But also there's going to be a lot more node-level parallelism. Okay, so to the fact you're going to have all these cores on a node, there's going to be a lot more node-level parallelism. You got to exploit data parallelism, and because of this more complicated memory hierarchy, your code has got to take data locality into account. Either explicitly or maybe hopefully the compiler will take it into account, but someone somewhere in the processing chain is going to have to do a lot to take locality into account. Now, when I think my friend Alice said exploit data parallelism, what she really meant is you need vectorization. You need really effective vectorization. So I want you to think about vectorization. And I love this slide. It's now out of date, but it came from my friend Kurt Koitzer at UC Berkeley. And those little pie charts there say, how much are you wasting if you don't take advantage of the vector units? So with SSC, you're wasting just 75% of the chip's capability if your code doesn't take advantage of vectorization. As you move to the 16-way SIMD that goes to 94%, of course, that's out of date because if I now double the amount of vector capability because I have two 512-bit vector units, it's wasting even more. So look, the bottom line is, it is vitally important that your codes vectorize really well. Okay, architects love vector units. I've never met a hardware architect who didn't love them. I've never met an application programmer who didn't hate them. All right? So this is an interesting tension that we at Intel are investing a lot of money and the industry is investing a lot of effort in figuring out how to really take advantage of these vector instructions. And so you have a few options with the vector units. You can let the compiler do the job, which frankly is what most people do. They get their program running, they multi-thread it, then they say, compiler, take care of the vectorization for me. And you know, that works sometimes, usually doesn't, but it's an option. The other thing is let the compiler with language level constructs take care of it. And this is really what seems to work well, you know, with the ignore vector dependencies, and this is why we have the SIMD construct in OpenMP. And I'm not going to get into arguments whether that's the right approach or the wrong approach. Look, I'm really just a stupid application programmer. But to me, whether I go pragma OMP SIMD or pragma IVDEP, ignore vector dependency, it's the same thing to me. I'm still going through figuring out what I have to do to restructure my loops so they can vectorize, and then telling the system, just vectorize the stupid thing. So that seems to be the approach that's really taking off. Now, I'm really bizarre. I actually like the third option, which is to use the low-level vector intrinsics. And so let's take a look at this using my favorite little example. There I am, washed up on a beach, waiting for a wave to pick me up again. I have a really bizarre kayak. It's kind of banana-shaped. It's really cool. At any rate, we're going to do the Pi program because it fits on PowerPoint and actually does something. And if you took the tutorial, you can see how much time I can waste on this single stupid little program. But, you know, here's what the code looks like. And we can vectorize this by putting the pragma OMP SIMD reduction. All right? And when I did this, it didn't do anywhere near what I expected. And I spent a lot of time stressing over this until one of my good friends, Robert Giva at work, pointed out that in C, your literals are double. So that 0.5 in the I plus 0.5 times step, that 4.0 over 1.0, those are doubles. So now I'm mixing doubles and floats inside my loop, which means I'm clobbering a lot of the opportunity for vectorization inside that loop. So I had to go through and explicitly say, no, let's make those floats. Okay? Now, I want to point out, the reason I'm putting this up on the slide is how many of you would have known that before I told you? Yeah, I mean, 3 or 4, 5? Okay. The second Robert Giva told me, I was like, yeah, of course. But, you know, because I knew that, but I didn't remember it when I was playing this code. You know, this stuff scares me with vectorization because it's small, little bitty changes that seem meaningless can have a huge impact on what the code's able to vectorize. And what the feeling is working with the vector units is you're having to reverse engineer the compiler to try and figure out what it is it can actually vectorize. I find that very, very frustrating. So I find this much better. and I know almost all the world's programmers would look at this and go, you've got to be kidding. But I actually prefer this. Look, I'm going to set up. what I do, if I'm doing a course on vector programming, I walk people through this. You know, step number 1, you unroll the loop 4 times, because I'm doing this with SSE. All right, so you unroll the loop 4 times. Then you set up your vector registers, okay, based on how you want the logic of the unrolled loop. You set up the vector registers, you build them, and then you do it as a sequence of operations on the vector registers. And then what you do is you try and decrease the number of temporaries by chaining the operations together. So you notice I have the application to the ramp, and I have the add and the multiply all in one section. Okay, so the code's really, really hard to read, but it's not that bad to work with. And at least I didn't have to reverse engineer the compiler because I knew exactly what I was telling the system to do. And I'm a control freak when I'm doing performance-oriented programming. I actually like this, but I understand most people don't. And then I parallelize this, okay? And once again, if this was my stupidly advanced OpenMP course that no one would want to take and we go through this would be pretty straightforward. So here's what I got. If I turned off vectorization, so I specifically told the compiler do nothing, this is the performance number I got right here. So it's like, 0.005 seconds. Then I just sort of said, okay, automatic vectorize. And I actually am really surprised. The automatic vectorizer did pretty darn good. It kind of cut the performance down roughly in half. Then I used the OMP SIMD, and it didn't do as well as the vectorization. I don't know why, but somehow it did not do as well. And then what I like about the effort I took with the SSE intrinsics is that's a realistic top bound of how well you can do. And so you can look at that and see that the auto-vectorize and the OpenMP SIMD didn't get to the same level as my SSE instructions, but they got into the ballpark. They weren't awful. So I find it encouraging. Now, I want to follow up with a slide that comes from a larger application study at Intel, comparing the explicit vectorization, that's at the OMP SIMD, to the auto-vectorization. And with more complex problems with people spending more time going through it, you can see that there are many, many cases where the SIMD directive in OpenMP really did help giving better performance, because that's that lighter color line. So it's got its place, and it helps sometimes. But I really find with vectorization, when I deal with it, and maybe I'm just more lame than the more intelligent people at Intel, but I always go through this process of stumbling around. You try the compiler, then you put the SIMD in there, and you muck around with this, and you figure out why I'm not getting what I want, and then I throw up my hands and go, heck, I'm just going to write the SSE. And I really am concerned as an Intel stockholder that as we're betting more and more on vectorization, it's not a pleasant experience for programmers. And we have a lot of work to do to try and change that. All right, so, hey, what about application portability? So if you look across the DOE community, from NERSC to Oak Ridge to Argonne to PNNL, you find that all these centers have fundamentally different architectures. And that actually will never change. And no one in their right mind would actually change it. It doesn't make sense for them all to buy Intel. They're going to always try other vendors. They're fundamentally different. But still we have to ask, given the high cost of building software infrastructure, we really need to be able to share software across centers. And we all know, I don't need to convince, I think, any of you, that the lifespan of a piece of software is greater than the lifespan of a piece of hardware. So it really is critical that software can move around to these different architectures, both between centers and between generations of machines at a center. And so this is a huge challenge, because if I have a machine that's a whole bunch of GPUs, or I have a machine that's a whole bunch of night landing, those are very, very different architectures. And it's very painful if I can't share software between that. So the community of programmers in the DOE and in the supercomputing community are really struggling with trying to figure out what's their path forward. And so they're having these workshops to try and pull together and learn best practices from the different centers to see if they can come up with a way forward that fixes this. But if you think about this from the application programmer's point of view, things are looking ugly out there. First there were vectors, and some of us old folk, there's a few of you out there that are old enough, remember the old Cray vector machines. And those were relatively easy. We just vectorized our loops, and they worked actually pretty well. In fact, I remember in 1989-ish, I made a bet with someone at Cray that their compiler couldn't beat my hand-optimized code. And I lost that bet. It was the first time a compiler really just beat me. And it just shows how advanced those Cray machines coupled with those Cray compilers were. And they were very different sort of vector units than we're putting on chips today, but they were really marvelous. But, the MPP revolution came along, the attack of the killer micros. And so they ripped out all that vector code, we, and put in message passing, which eventually became MPI. So a very painful adjustment. Then, of course, multiprocessor nodes came along, and so people added OpenMP. And according to Alice and Company, it didn't really do very much. And according to Alice and Company, OpenMP only works on a smaller number of nodes. And, wait a minute. Scaling is a factor of the algorithm and how you use the API. I don't really think it's fair to say an API is fundamentally unscalable. If it is, the people who designed it were bad. I look at a lot of codes, and I haven't looked at the NERSC codes, so I haven't looked at the codes that Alice and her colleagues were thinking about when they wrote that. But I've had multiple meetings with people at these DOE centers, and what they did is they took their MPI code and just put a parallel 4 in front of a loop. You mentioned this, James, earlier today. If you're going to do that, you're not going to get good scalability, period. I'm sorry, you're not. Okay? Let's face it. If you want good scalability, you have to look at your algorithm. You have to think about the data structures. You have to optimize the data structures, the layout. You have to move the parallel overhead out. And to think that you can walk up and just put parallel 4 in front of every loop nest and expect that you're going to get reasonable scalability, it ain't going to happen. I think the weakness of the GPU world is also its strength. Because when you come to a GPU-based machine, you're going to have to rewrite code. You're going to have to hand optimize that kernel from scratch. And so you accept that and you do it. And in essence, with OpenMP, we kind of sell people this idea that, you just sort of, put a parallel 4 here, put a parallel 4 there, and you move from your laptop to a Xeon Phi. We say this all the time in our marketing literature. And, it's one of these things where it's partially true. But, do you really believe a code you optimize for 2 to 4 cores is going to optimize and run well on 60-plus cores? No. So, we really have to be careful here. So, I'm sorry, my friends from NERSC. I have to take a little bit of offense at that statement that MPI plus OpenMP doesn't really work and it only scales to a few processors. Look, if you're willing to do the work, it will. All right. Okay. So programming models by the dozen. So, if you're an application programmer and you look out there right now, it's a confusing space. And Alice kind of draws this wonderful analogy to Mozart in a conversation with Emperor Joseph II. My dear young man, don't take it too hard. Your work is ingenious. It's quality work, but there are too many notes. Just cut a few out and it'll be fine. Mozart's like, well, which few do you have in mind, Your Majesty? Apparently this conversation occurred when the Majesty found, the Emperor, that he couldn't play the music that Mozart was writing. So rather than figure out how to improve his playing, he just figured out Mozart could get rid of some of the notes. And so I'd love to be a king and think that way. But, I've used these slides before, but I have a point I want to make. This is a list of programming models in the 90s, all right? And it's a ridiculous list. But this is what happens if you leave computer scientists and vendors to their own will. Okay, it's fun creating a programming model, and we will do it. Now, I want you to look at this list and think about the amount of human effort and engineering skill wasted. Okay? Think about how primitive the tools are when you come up to the system you're working on, and you go, oh my God, why can't I have a portable debugger as I move from one system to another? Well, how can your portable debugger team develop a technology if they have even 5% of these they decide to support? The point I want to make is it's not just the wasted effort in creating all of these different programming models. It's the wasted effort in the tool chains that do not get matured and are not made available. So this is incredibly damaging. Now, it's even worse, and once again, I apologize. Several of you have heard me use this slide before, but if you haven't seen it, this is very important. There's a human phenomena called choice overload. Okay? How many of you have heard of choice overload? Good, not too many of you, so I'll only bore about a third of the room. This was an amazing study. It was done at the Draeger grocery store, which is over in Palo Alto, which is the neighborhood around Stanford. It's a lot of rich, upscale customers, and so it's a gourmet grocery store. And so this research department at Stanford University did the following. They put out a display of gourmet jams. One display had 24 jars, the other display had 6 jars. So you can just kind of imagine, 24 jars, yeah, big and lots of stuff, 6 jars, just a little tiny thing. All right? You could go and sample the jams, and then they would give you a coupon, which would give a discount if you buy. So think about what they could measure. They could measure how many people walked by the display, how many people were interested enough to sample a jam once they walked past the display, and how many people subsequently purchased jam. And these results are amazing. The bigger display got more attention. Who's surprised? But only 3% of the people who sampled purchased jam. Whereas the 6-jar display, 40% stopped and looked at it, but 30% subsequently bought. That's a dramatic number. Now, they've repeated this study several times, and what this shows is that human beings, when presented with too many options, they choose to not choose. They're overwhelmed. It is called choice overload. You overload the human choice system, and you go, oh my God, and just walk away instead of making a choice. All right? Now, the retail world has learned this too. I bought a bunch of furniture 5 years ago, and I really noticed the place I bought the furniture from had 3-bedroom sets, 4 living room sets. And I would go into places that had 5 times that number, and I couldn't decide, I couldn't buy. So it really works. So think about that, and now look at this slide. And think, what did we do when we created this profusion of programming languages? If we're trying to attract application programmers to parallel computing, what did we accomplish with this? All right, so this is a serious, serious phenomena that vendors should be concerned about, but also you application programmers who are trying to create a world where you can have a dependable environment when you move from machine to machine. Think about what this does. Now, 2005, I was so excited, because by 2005, things were looking better. If you wanted a thread library, you had the Win32 API. If you were in the Windows world, you had POSIX if you were elsewhere. If you needed directives, you had OpenMP. Done. No other thing to discuss. We had MPI, great. We knew we needed something for the managed languages. There's X10 out there, and maybe Java concur. But it was a very small list, and life was simple then. GPUs were around in the academic literature, but no one took them seriously back in 2005. Okay, that changed shortly thereafter. So I figured we had learned our lesson. Well, I sat down for an afternoon and looked through computer conference proceedings from 2010 to 2012 and look at the list I came up with. I didn't even spend a long time. This was just flipping through, looking at the titles of papers. And these are the programming models that they were talking about. So somehow we have slipped back into this mentality of you have a new problem, create a new programming model. I want a PhD. I know, I'll get a PhD for creating a new programming model. All right? And so it's out of control. And the human waste of this just burns me up. And it happens, it happens several times. It happens every other week or so, sometimes more often. Someone comes up to me and says, what programming model should I use? I'm interested in heterogeneous platforms, and I've heard about this OpenCL thing, and I know you know a lot about that. I've heard about this OpenMP thing. I know you know a lot about that. What programming model should I use? And I have to stand there and tell them I honestly cannot tell you, because I don't see the support around OpenCL that I thought would blow up, that I thought would take off. And the fact of the matter is, today I cannot write an OpenMP program that runs on a GPU, a CPU, and an FPGA. I can't. Maybe someday soon, I hope, but I can't. So we've really, really mucked it up, and it bugs me, because I thought we knew better. Oh well. So what's gone wrong? That's me rolling off a bridge. It was really fun. Hurt like heck when I hit the water. But I'll tell you what happened. In the 90s, the application community was united and were aggressive. Now that happened partially because government funding was channeling through a small number of programs, and the people playing a leadership role in these programs were kind of left-wing liberal sorts who were really into union organizing type ideas, and they brought programmers together to snap the whip. And it made a difference. If you look at the history of the creation of MPI, the applications community pushed very hard for it. Vendors were happy to go along, right? If the applications community are lining up and saying, we need you to do this, 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 and this, and we'll buy your machines, vendors are like, okay, yeah, we got it. We actually like it when the application communities come together and push around. But when MPI came out, the applications community used it. They committed to it, they worked with us, they worked with the MPI forum, they used it, and that got it off the ground. They didn't keep using NX, even though there was a while there where the Intel native message passing was superior to MPI. Applications community was like, we don't care. We're not using that proprietary thing you guys have for us. And it made a difference. Within a year, MPI was everywhere. Okay? OpenMP, exactly the same story. Applications community got together. My hero, Mary Zozel, I'll remember her for the rest of my days. You know, how firmly she would be saying that. You will do this. You vendors will do this, and you're going to work together with us. You're going to create this, and we're going to get it written into the RFPs. And you know what? The application community lined up behind it. And within a year of the spec coming out, OpenMP was available everywhere. And you, an application programmer, could walk up to an IBM, a DEC, an Intel, an SGI, a Cray machine, and have one program that you could recompile and run there. This was marvelous. So users, when you let vendors lock you into a platform, you're hurting yourself. What do you think you're telling the vendor community when you use CUDA and OpenACC? What are you telling them? You're saying, hey, vendor, we're quite happy to lock ourselves to your platform. Yeah, thanks, vendor. That's really cool. Now, let me be clear. I just did a slam there at my friends from NVIDIA. Are they acting wrong? No, it's a market economy. This is capitalism. Capitalism 101. If I can lock my platform to my customer, I can sell them more stuff. And I like that. All right? So it's not that the vendors are evil. You know what? Intel would do exactly the same thing if we thought we could get away with it. And maybe sometimes we try it. I won't go there, though, because I work for them. But in other words, don't take this as me saying, NVIDIA, you're evil and you're wrong. Okay, I don't want that message, because it's not fair. They're doing what they should, which is, how do we make as much money as possible from these customers? So it really is up to you, applications community. And I'll come back to that later. All right, back to Alice's slides. Okay, so an application programmer, when you look at this world and you look at where application programmers are, try and think hard about the world that they see. They have these different programming models. They're tied to different architectures. You know, OpenMP doesn't work with FPGAs yet. And if you're tied to that, you're stuck with whatever OpenCL environment or whatever you have to work with there. I mean, application programmers live in fear that the language they're going to choose, and they spend a lot of time learning this language, that it's going to become unuseful for the platform they need to move to. And they're going to be stuck. So at any rate, you really need open standards, you really need open vendor-neutral standards, and you need the community, instead of running off and creating new programming models or running off and supporting new proprietary standards, you need the community to commit to the hard work of supporting the open standards. And it can be hard work because you never get it right out of the chute. And rather than just walk away and go, well, you guys don't support accelerators, I'm going to go and create my own standard. No, you roll up the sleeves, you buckle down, and you figure out how to get the accelerator support you need into the standard. So at any rate, you know, portability is difficult. No one's saying it's easy. But if we move towards open standards, we can at least build a software infrastructure that will move forward and sustain us across generations of machines. Now, people often talk about performance portability. I get, because of my background with OpenCL, my friends at Intel often tease me about OpenCL is not performance portable. Well, we don't have performance portability today. It doesn't exist. It doesn't exist with serial programs, all right? It's not there. It will never be there. It's never been there. The issue is not performance portability, all right? If your goal is a large fraction of peak performance, you know what? You're going to have to specialize, period. That's the way it goes. But there's some pretty good performance portable environments out there. OpenCL does a pretty darn good job. And what time am I supposed to be done? 5 after? Oh, 5 after the half hour. Okay, good. Then I'm not going to go through these slides in great detail, but they'll be available to you. Well, actually, my chapter in the first volume of James' excellent Programming Perl books develops this example. And we did a matrix multiply, and I walked through in detail of how we did it. None of this, it's an exercise for the reader. We show how we transformed the loops. We show how we turned it into a multiplication over blocks. We explain how this code works. Now, if any of you have done dense linear algebra, you know how long and complex an SGEM can get, right? All right? This is nothing compared to how complex it can get. It looks a little complicated because I have to put logic in the OpenCL code to figure out which piece of the matrix I'm operating on, and to figure out what offsets I need to get to the next piece. So that's what the ugly logic is. All right? But it's not that much. And notice there's no assembly code in this anywhere. I'm doing this all in the high-level kernel code. And look at the performance I got. All right? Oh, gosh. My little block there blocked the A and D number. That wasn't deliberate. Once again, this is what happens when you don't get to use your own laptop. Delete. Don't you have a delete key on here? Man. Okay, I know I can't complain. I'm in Germany, so of course it's going to be a German keyboard. Oh, my goodness. Okay.
Entfernen.
Entfernen, yeah, okay. Look, I just want to put this up here because, you know, this is an amazing level of performance portability. That a single program just recompiled as I move place to place, doing dense linear algebra. I'm getting 12 gigaflops off my silly little laptop. I'm getting 74 gigaflops off my Xeon Phi, 38 gigaflops after the graphics card on my laptop, and 119 gigaflops off my NVIDIA Tesla. Okay? And this, I'll get you in a second, okay? And I'm not trying, I mean, I know I could get more. I've written professional math libraries. I could assembly code the kernels. I could call BLAS. Okay? There's a lot more I could do. But that's amazing performance. I've never seen that kind of performance portability out of OpenMP ever. All right? I've never seen anything with that level of performance portability. So I'm trying to tell you, there's stuff out there that does excellent performance portability. And yes, I was going to go on, but do you have a question?
I get your point, but block size equals 16 is not exactly what we want.
Okay, I had to change one parameter for block size. That's it. Just one. All right? Okay, well, you know, do it. Show me. Going to a GPU and a CPU, getting this kind of performance portability. And that's the box. Actually, the box I removed, that's what it said. It said, you know, I look forward to trying this with OpenMP 4.0, because it can't do it today. Going from something as radically different as an NVIDIA GPU to a Xeon Phi to a CPU on my laptop to the Intel graphics card. Going across all of those, and that's getting about 25% to 50% of the MKL number on the Intel parts. Pretty amazing from high-level code. So performance portability, and this is a slide from Simon McIntosh Smith showing that, yes, he did it with real applications as well. Because I understand, come on guys, DGEM? Okay, but the point I want to make is this focus on this mythical quest for performance portability completely misses the point. Because application developers who are looking to get a major fraction of peak performance know they're going to have to mess with the code. They know they're going to have to optimize moving platform to platform. I hear many of my friends in the programming environment side say, oh, they have to maintain a different kernel for each platform. It's like, yeah, so? We've always had to do that. You know, I moved to a different architecture. I call a BLAS library tuned to that architecture. Why? Because they need a different kernel for each. What's your problem? Okay. The issue is not performance portability, really. I often hear that from people who just want to discount some new kid coming along like OpenCL. No, the issue is maintainability. I have to be able to maintain a software base. And that means I need a single software infrastructure that works everywhere that I can maintain and support over time. And maintainability is the key. And that's what we want. A single common code base that is portable between platforms so I can maintain that software and not have to rewrite when I move place to place, but just optimize a few kernels here and there. All right? And I'm out of time, but there was this DOE applications workshop where they're collecting information on where people are going. People are just dying to get their hands on OpenMP 4.0 with the target directives. All right, vendors, please get busy. We need it out there, and we need it out there across platforms. People are eager to play around with it. The accelerator directives, there's a huge amount of interest for people to play with that. Even though they may recognize they have to have different sources between different platforms, fine. If I can support everything from one code base, my life is much, much better. Okay? And this is a case study on a particle and cell fusion code. And we don't have time, but I just wanted to point out that, it's a real production level code. They played around with CUDA and Fortran, and they've even been going through and experimenting with if-defing in between OpenACC and OpenMP. The idea being that OpenMP is not there yet in broad deployment for the accelerator directives, but they can learn an awful lot about algorithmically what they need to do playing with OpenACC today. And then they can switch between them with just compiler directives, so they can do a macro in the make file and generate the OpenACC or the OpenMP. And so I am looking forward to the day when I can just say, throw away that OpenACC and just dedicate yourself to OpenMP. Life will be better for all of us. So common-based software is absolutely critical. We want to get towards performance portability, but the real goal here is maintainability. And for that, the DOE is aggressive in investing in standards committees, and we can produce the same standards. It's very interesting. I don't know how much time any of you spend in the MPI world, but MPI is add shared memory. There's something we have found incredibly fascinating called fine-grained MPI, which allows me to do the sort of stuff I used to have to do OpenMP with for managing lightweight threads on a CPU. And so one model we're doing a lot of interesting work with is there's, the standard model of HPC is MPI plus OpenMP. We're finding a lot of success with MPI plus MPI. So a lot of interesting stuff going on in that MPI space. So it's moving very quickly. So, in summary, look, we all know one size does not fit all. We made MPI work eventually, but you have to work on different programming models as you move around. And it may be that no one heterogeneous architecture, programming architecture will cover all environments. It's not necessarily the case that you're going to have to do everything with just one programming model, but we need to get close there, and whatever we use needs to be standard. All right, now, I just want to summarize with the comments I made. I think we're in bad shape, and I think it's the fault of application programmers. We live in a market economy, and you have to recognize that your interests are not always the same as vendors' interests. All right? Not because the vendors are bad, but because they want to make money. So anytime you reward a vendor for bad behavior, you deserve what you get. All right? Don't come whining to me. You deserve what you get, OpenACC and CUDA programmers. All right? So what I am calling for is a revolution. I want you application programmers to unite and take control of your destiny and stop letting vendors push you around by getting you to use proprietary standards. As we found in the 90s, when the applications community united behind open industry standards, we had a better world. Please do that today. I work for a vendor. I can't do it for you. Only you can do it. And until you realize that you have real power when you join together, we're going to continue with this throwing out new programming models all the time. And we all need that to stop. Okay, that's it, I think. Well, that's it. Yeah. I don't know. There's so much more work to do. We've actually had some conversations with some of the folks in the DOE national labs who've come on and said that, look, we have to use this barrier-centric programming model. We have no choice. It's because of the way the code's been factored, and we're not going to refactor our codes radically. So vendors, can you please have a runtime and compiler that removes the barriers for us? Can you have an analysis that you do that says, oh, this barrier is redundant, I can understand that. Much as we have compilers that look at data dependency analysis and figures out how to vectorize, couldn't we build compilers and runtimes that remove those excess barriers? And I think that's something that has to be looked into. I don't know if that's something that can be done at the standard level. You know, that's something, though, that can definitely be done at the runtime and quality of implementation. I don't know. I don't know. I'm an application programmer, not a compiler person. So, you know, it's an interesting question, is the specification as written, will it support that sort of thing? I mean, this is the criticism that people have at OpenMP, and I first heard it from Arch way back when he was first starting work on TBB, Arch Robison. How OpenMP exposes the threads, and it doesn't say it would be nice to have some threads, it says you will have some threads. And it doesn't say it would be nice if the data laid out like this with the threads, it said you will have the data laid out like this. Which means you've tied to the hands of the runtime to do an awful lot of work, like work stealing, like using different numbers of threads so you can have composability. So there's a philosophical gap there. You know, it could be OpenMP, we've gone too far, and it may be we need to add in the spec. I've been thinking about this. You know, we have the num threads clause on a parallel region that can take an integer expression. What if it could take a handle, you know, auto? You know, you give it a keyword, which is your programmer's way of saying, runtime system, I would like you to get really, really aggressive. And it's okay if you relax the rules on the threads and exposing the threads. I mean, I don't know. I think that's a conversation, though, that the standards committee should have. Because, you know, the folks coming outside looking at more descriptive approaches, they're onto something. And we're seeing this in the exascale community. You know, if you look at all the work towards asynchronous multitasking for extreme scalability, it also comes down to that same thing, is if you over-prescribe everything, you don't give the runtime room to modify and adjust the hardware going away and coming back. So, I mean, it's something to think about. No other questions? I wasn't controversial enough? I'll have to try harder next time. Really? Oh, no. I don't want to sound like him.
Okay, well, Tim, thank you.
Okay.